Any questions? Okay, y'all have your exams back, look it over. Don't forget to, be meeting with me, anyway, and some more resources will be coming up. Okay, let me remind you, the last thing we talked about was so-called Zorn's limit. It's equivalent to the action of choice for prior improvement. To that, it says this is a partially ordered set. Let me recall for you, those of you that this isn't on the time. You gotta remember what a partially ordered set is? This is sometimes called a fill set. It has partially ordered set is I don't know, but you might remember what a partially ordered set satisfies. The transitive, anti, and reflexive.
Yes.
Reflexive. So let's go through it. That means for all A and A is always less than or equal to A. Two, A is less than or equal to B, and B is less than or equal to A. Implies what? Really common sense study from your knowledge of, say, inequality and reals. Right. It's the same best symmetry, and it's transitive. So, for example, take the real numbers with the standard ordering less than or equal to 5. Any two integers in two real numbers, A is less than or equal to A is less than or equal to B, and B is less than or equal to A, means they're the same, and you have transitivity. Right? This is actually a totally word set. Because if I take two real numbers, one of them is less than or equal to the other. So everything in the real is apples, they're all labeled to be compared. Well, yes. Let me give you an apples and oranges. This is a good example of a partially ordered set that's not totally ordered. And this is a nice segue. That's there. By this, I mean the power set of the set 1, 2, 3. So that's the set of all subsets of 1, 2, 3. How many subsets are there? A set of 3 elements. You better remember? 6. 2 to 3. So there's a action. And I'm actually going to list them to show how the things work. My arrows are pointing from big to small. So that means this is contained in this. This is this. And the more subset. This is an example of partial order. Not totally. Yes.
Can you also draw lines to all the other sets?
Well, for example, you could draw a line from this one to this one.
Oh,
That is correct.
But
Yeah.
okay.
But I don't want to muddy the water, so I'm going to use transitivity since this one contains this, and well, let's see if I want to pick this one. This one contains this, which contains this. Yeah. Everybody okay with that? But notice there are apples and oranges here, namely this and this. Neither one of these contain the other, right? These two right here, apples and oranges, neither one contain the other. But whenever you get containment, it's properties. Right? What Zorn's lemma says is if you have a partially ordered set, like keep in mind that last example, and every chain has an upper bound. Now, a chain is a totally ordered subset of a partially ordered set. So even though this may be apples and oranges, I'll give you a group of apples. This right here is a chain inside this partial ordered set. Do I agree? Because all of these elements in the chain are comparable. If I take two elements of this chain, this one's containing this one's containing this one's containing this, and so forth. Any two can be. Everybody open? Okay, with that in mind, I'm going to give you all a pretty huge theorem here. This is 9310. Let R be a ring with a joint. And I and R and I. Then I is contained in a minus one. This is a huge, huge theorem. And it depends on the axiom choices. It depends on Zorn's limit. If you have any ring with identity, then any ideal, any proper ideal, that's clear, a proper ideal, that I is contained in the maximal. So any ring with one has a maximal. In particular, what's the corollary to this? And I'll prove this one theorem as well. For example, I equals 200, the ideal term about 210. Stop here. James 210 is contained in fact, this ideal is contained in 4 different maximal ideals. The ideal derivative of 2, the ideal derivative of 3, ideal derivative of 5, ideal derivative of 7. Let me also point out that for any of these containments, there are other ideals in between. For example, the ideal derivative of 14 is in between here and here. But these are contained in these 4 maximal ideals. For most beginning examples, maximal ideals are fairly easy to find. Any finite ring must contain a maximal ideal because there can only be finite ideals. So all you have to do is just stack them up and see which one's the biggest, so to speak. Let's prove this. But here's the thing, it does require the axiom choice, even though this example is fairly obvious. And I'll give you an example that's less obvious after this. But I and R be proper. anyone you want, as long as it's not all R. And here I'm going to define, here's like, I'm going to define a certain function for the set. Okay, here's my set. I want my set S, my partial order set, to be the set of every ideal that contains J, but it's still R. Right? So this is a collection of every ideal that contains I and is still a proper ideal. This is a partially ordered set, right? Because take two J1 and J2 ideals that contain I, right? Well, they satisfy everything that that we need here. So our containment is right. So this is just a collection of ideals. This is a collection of subsets of R, ideals in particular subsets, and we order these by containment. We say that J1 is less than or equal to J2 if J1 is contained in J2. And there may be many ideals that aren't comparable. Like, for example, if I look at all the ideals that contain this, right, two of the ideals would be 14. 14 buys that, so, and also 6. But neither one of these ideals contains together, right? Because 6 doesn't divide 14, never divides 6. So this is a partially ordered set. And, oh, you know what? Guess I should probably convince you that S is not empty. I don't want to send it up here during the next, spend the next however many minutes proving theory about the empty set. S is also not empty. Anybody see some has to be an S set of ideals? They not for product.
You had ending?
No. I accept.
That's a,
I certainly can, is contained in I and it's proper ideal class. So S is not, so I'm doing this. Now, let's take a look at Zorn here. Zorn's speaking to me. It says, if you have a partial ordered set, which we have, and it's got the property that every chain in S has an upper bound. So let's let let this be a chain. So this is just some collection of ideals that are pairwise common, right? Yes.
is that a C?
Yeah, it's like a curl C chain. This is a collection of all. So for example, this might just be one item. If it's just one ideal, it's certainly a chain because it's comparable to itself. Or it might be 27 items, or it might be infinitely, might be a very big index set. But this is a chain of ideals that all live in S. So every one of these ideals is proper and it contains I. And something else, J alpha and J beta are in the chain, then J alpha is contained in J beta, or J beta is contained in J alpha. That's the chain, right? If I pick two ideals out of S, I might pick an apple and an orange, and you can't compare them like these two. But I'm picking a subset that's totally a chain. And so what happens is pick two of them out, they're both apples. This one's less center equal, this one or the other. Okay, deep questions. We need to show that that chain that I've got has an upper bound that's in S. Anybody want to guess what an upper bound of this chain could be? I want an ideal that's in S that contains every element of this chain.
Yes,
What's that?
would be yes.
Oh, right, but here's the problem. That's a good idea, right? Because you're trying to grab everything. I get that. The problem is S is a collection of a bunch of ideals. I want a single item in S that contains it. But you might be onto something. Come on, guys, if I got you all together in one room, the union of you all can figure out this. Okay, why don't we try that? Now, word of warning. We saw back in group theory, unions of groups are almost never groups, right? I mean, that was a big thing to do, right? But I'm gonna try this. I'm gonna take this whole freaking chain. And I'm gonna take the union of all the ideals in it. Right? Now, notice that for all alpha and gamma, maybe alpha is contained in U. Because that's how we built U by union of. So any ideal in there is contained in, right? So U is an upper bound. Because any one of that elements of the chain is contained in its union, right? Quite agree with that? What's the big question that I've kind of glossed over we have to address this?
I was just gonna ask if that means that, couldn't you be in the chain already?
Could be. Right, in fact, if the chain is finite, then you will be in the chain. Right. Here's what I don't know. I don't know it was an element in S, right? I know it's an upper bound as far as a set goes, this collection of things contains all the J alphas, but I don't know it's still an element of my set S. And what does it take to live in S? What's the HOA for living in S? Well, you've got to be a proper ideal, right? And you have to contain I. Well, I've got that part. Well, notice that for all alpha, I is contained in J alpha, which is contained in U. Right? Right. So U has this property that U contains I, right? That's one of the things we need. What else do we need? We need the U as an idea. And let me emphasize again, we need you to be a proper ideal. Right? Okay. And this concerns me because unions of groups don't even have to, in fact, railroads. But actually, you've got saving grace here because this is a chain. So I claim he was an I. There's two things we gotta do. We gotta show that it's a subgroup, we gotta show it's back, right? So let's let. I agree. Stick to it all of a sudden. And let me also point out, U is not empty. We know that because I is contained in U. Right? Right, okay, so far. Now, how do we make U? It is a union of a bunch of ideals, right? So that means that this X and this Y appear in this union of ideals, right? So there exists alpha and beta in my index set such that X is in J alpha and Y is in J beta. Everybody okay with that? Because U is the union of all these, so if X is in this union, it's got to be a one of the J alphas. Y is in the union, it's going to be one of the J betas. And what do we know about J alpha and J beta? This is crucial. Was it?
One of them contains the other.
Right. We say, without loss of generality, that J alpha is contained in J beta. Right. Therefore, X, Y are in. If J beta is the bigger one, X is down here and Y is up here, so both X and Y are in J beta, right? Therefore, X minus Y is in J beta, which is contained in U. So actually the union is a subgroup. Because given any two X and Y in there, X minus Y, subgroup right here. Also, if X is in U and R is in R, then X is in J alpha, some alpha. Therefore, R X and XR are both in J alpha, because J alpha is an ideal. And J alpha is in. So. And there you go. What we've shown is every chain in that set S has an upper bound in S. So by Zorn's lemma, S has a max bound. Yeah. I'll call it M. And I is contained in M because every element in S contains I. So we've established the first remark in the theorem. We've shown that any proper ideal is contained in a maximal. I agree with that. The other remark I said is, oh, so in particular, every commutative ring with identity has one. Let me show you how cheap this is. Let R be, actually don't do commutative ring with identity. What's the easiest ideal, two-sided ideal in R that you know that's proper?
The identity. I mean, zero.
That's
Zero.
right. See,
Well, I mean, it has an identity.
everybody, I think, would have to agree this is a two-sided ideal. By previous, I, I zero contain maximal. So all we need to do is use the zero ideal as a C, then it's contained in this. And then, but the previous statement is even stronger because it says you can use any proper ideal as your C, and it's contained in some types of ideal. Okay, any questions on? it? Yes.
Does that mean that we showed that every chain has an upper bound? So it's, does that mean the ring can have multiple maximal ideals?
Bet.
Okay.
Let me give you an example. So I'm glad you bring this up. This is one of my favorite examples. Let me point out that if your ring does not have, an identity, then you may or may not have a maximal ideal. That identity. Oh, there's one thing I did. I left something out of the. What's one thing I didn't prove about this? I'll finish this up. You guys are probably wondering why all this identity stuff. I left out one detail. There's one other property. We proved that U has an ideal. That U is an ideal, right? So we'll start here. Let me not show that. I forgot to show U is proper. Goodness.
And just focus on seeing if I use the homework strategy before it, homework 12, because I find it very interesting.
We don't. Let me give you guys a hint. I don't know if you remember this, because actually the hint is very important on the fact that my assumption here is ours ring with identity. An ideal is proper if and only if what? Doesn't contain the identity. Because if it's proper, well, if it contains the identity, then it has to contain everything, right? Because it's an ideal, it's vacuum there such that it can.
It doesn't, then it doesn't have to count.
That's it. Right. So let's suppose. And let me remind you how this was defined. Suppose one is in this U. Now U was constructed as a union of these J alphas. So if one was here, it must look like some of the J alpha, right? Well, what does that mean about J beta? That's right. And this is a contradiction because in our set, we define these ideals to be proper ideals, right? So all the J alphas, J betas, they all have to be proper. If U is not proper, that must mean that one was contained in one of the J alphas, making it not proper. Right? So one is very important. One is very important. I'll give you an example. Like I said, if you have an ideal that doesn't have identity, it may or may not have a maximal ideal. You might think about this. Let me give you this. What's the R?
You said that it's constructed using proper ideals, but I don't remember that from our previous thing. I've been set so that way.
So what's this now?
You're saying here that it's a contradiction because J beta is not proper, but
If one is in J beta, that would mean J beta is not proper.
right. No, I get that part, but why is that a contradiction? You said that.
Look back at the definition of the set S.
J proper.
Right. Those J's have to be proper.
Okay.
I want to look at this ring right here. This is an infinite direct product of Z2, so a typical element here would look like. Going on forever. So you might think of this as sort of a countable vector. And all the entries are 0 and 1 out of Z2, and you've got complete freedom of how to do this. By the way, what's the identity? I describe the identity of this line. We're adding and multiplying just component lines.
Oh, just once.
One across the board. That's why. Would this be a ring with identity if I change this to direct sum? Anybody remember what's the difference between the direct sum and the direct product? That's right. In the direct sum, you can only have finitely non-zero entries, right? So if you look at the direct sum, that wouldn't be a ring with identity. In fact, it's an ideal. Okay, let me list some maximizers. Of this. And then I'll give you a challenge. Look at this ideal. M1. This is the subset of the direct product where I just demand that the first quarter be 0. Everything else, do what you want. Everybody else should. Would everybody agree when I add two things to that form, it's of that form? Right? Because you still have 0 front. And notice it's vacuum because when I multiply any element of the ring times this, it's still got a 0 in the front. So this is an ideal. Everybody agree with that? And in fact, it's maximal. Here's why it's maximal. Because pick something I want to try to make this ideal slightly bigger. Pick some x that's not an even 1. Then x is in the form 1, alpha 2, alpha 3, alpha 4, like that. Everybody agree with that? If I pick something in that ring that's not an M1, I know it has to start with a 1. Because everything that starts with 0, it's in the maximum, right? Everybody agree with that? Notice that is an M. M1. So what this is basically this thing reads this, and this new element here, this entry is 0 if this is 1, and it's 1 if this is 0. Do I agree with that? So what happens when I have x plus y? What do I get? What happens when I have x and y?
Scale 1, so I can get it.
Yeah, is it? So the ideal generated by x and m is all of R for all x not and m. So M1 max. Do I agree with that? Because any ideal that's slightly bigger, if there's even one more element in there, you've automatically got the identity in there and it's the whole range. So you can't shove another ideal in between M one and R. Everybody okay with that? But everybody also agree that there's nothing special about the first chord. Right? I could have done this. Or epsilon one, epsilon n minus 1, 0, epsilon n plus 1. So I can make another maximal ideal by letting 0 be in the nth coordinate and complete freedom of other. Right? These are all maximal ideals, same proof. Here's my question. Are those the only maximal? How many of you? Think that's it? How many of you think there's another maximal? Anybody? Now, how many of you can write another maximal ideal out?
Yes. What if you have 2 zeros?
Nope, that won't be maximal. It's got small. In fact, I'll go you one step further. Anybody that can explicitly write down a formula for a maximal ideal that's not one of this list here, I'll give you an A in it for it. You don't have to show it. Just give it to me, write it down. And let me show you why this is difficult.
But you're saying there is one.
There's uncountable, and I can't write a single one like that. And that is why Zorn's lemma is actually doing this. Let me show you how this works. On 0, 7, 4, that goes 5. And everybody remember the direct. So in other words, everything in the direct sum does some stuff for a while. Everything in the direct sum in this setup has to end in an infinite string of zeros. Do I agree with that? Everything has to end in an infinite string. This is an ideal. Because if you add 2 elements to the direct product and they both end in an infinite string of zeros, then there's some as well. Do I agree with that? And since we're multiplying component-wise, if you multiply something into an infinite string of zeros, and you multiply by something else, your infinite string of zeros will be at least that long, right? In a certain sense. Everybody okay with that? This is an ideal. Zorn's lemma I is contained. No, anyways. But it can't be any of these. Right? Because, for example, in the infinite, in the direct sum, I have 1 and then all zeros, right? 1 and all zeros is not an M1. In the direct sum, I've got 0, 2, and then all zeros. That's not an M2. You've got 0, 0, 1, and then zeros after that, so it's not M3 and so forth and so on. So this thing is not contained in any of these maximal infinities. So there has to be another. There has to be. And here's another problem. And this is why axiom of choice. This is everything that ends in strings of infinite strings of zeros, correct? There are countable many things in this ideal. This ring is uncountable. So you might ask yourself, is this in fact the maximal ideal? And the answer is no. You can make this a little bit bigger by looking at this is an ideal that properly contains I. This has everything that ends in an infinite string of zeros, and then I add this one more element, alternating zeros and ones. Now you might say, hey, Jim, is this the entire ring? Can you get the identity? But you can't get an identity by adding this to this, because there's no way you can get an infinite string of ones, because everything in here is in an infinite string of zeros, and these always alternate. And I guess on the even entries, you have zeros. There's no way to ever get an even this forever, right? Well, now that you've made that choice, is this maximal? And the ideal is no, but you have to make more choices, right? You can't now throw in the idea, you can't now throw in the element 0, 1, 0, 1, 0, 1, because when you add those two, you get the identity. But there are other things you can throw in, and you have to start making infinitely many choices. So actually, as it turns out, this ideal actually is contained in uncountably many maximal ideals. And there's not a single one of them that I can describe, right? They're all there. So what this demonstrates really is Zorn's lemma. It is doing something in many cases that's pretty non-trivial. Okay, any questions? Yes, sir.
This is something you probably explained in the class that I missed. I'm noticing using the parentheses for a lot of the stuff with ideals. Is that something, because I didn't see that in the notes, is that something you explain?
What I meant by here is, what I mean in this notation.
Well, actually, this is probably not the best time to bring it up. Yeah, because here you're just talking about it like a tuple.
That's right. Yeah, I'm talking about a line tuple. That's right. Let me give you any other questions? Yes.
So would we want to like just keep adding elements that like correspond to like decimals or of real numbers?
Oh, you mean, are you trying to build this thing?
Yeah.
Yeah, good luck with that. Yeah, effectively do this. Are you 21 yet? I'm glad to be able to preparing to effectively tackle this. Yeah, but it's hard. It's very hard because you're making choices. I didn't have to add this particular element. I could have like gone 1, 2 zeros, 1, 2 zeros. There's various things like that. Well, when I make that choice, that influences my next choice. Unfortunately, there's infinitely many to be made. So good luck counting. I mean, if you come up with some clever way to do it, let me know. I'll give you an A in the course and steal your results. So, yeah. We say that R is reduced. I can make this definition, I guess, in general, but I'm using the bring it by this. If R has no non-zero nilpose. So let me give you an example or two. Any integral domain is reduced. Because after all, an integral domain has no zero divisors at all, other than zero, let alone nilpose. So for example, Z. Z6 is also reduced. 0, 2, 3, 4 bar are zero rises. But only 0 bar is no problem. So you can have a ring with zero divisors that is in fact reduced. And there's a natural way to pass from any ring to a reduced one. Let me give you this following theorem, which is very useful. Let R three is very important. Emphasis. A proper. Okay, this is actually very useful. I is maximal if only hormone I is.
That's also maximal. Or prime.
Yeah, but those are adjectives to describe ideals, not rings.
Goes max.
So I is maximal if only if this ring has. You might want to take a step. That's coming out. This is actually.
Oh.
Two. Is prime. If and only if R mod I is. Well, I'll take a stab at that. And equal to lane. And 3. I is radical. If and only if R mod I. Okay. This is actually very useful because sometimes it's fairly easy from the computational context to determine this. Let me give you a corollary. Let R be what? Given the conditions. One, maximum. B, prime. 3, radical. We have 1 implies 2, and 2 implies 3. So in other words, any maximal ideal is prime, and any prime ideal is radical. And this follows immediately from this theorem, because if R mod I, any field is an integral domain. Right, because your fields can't have any non-zero zero. And any integral domain is reduced. So that means maximal plus prime and prime plus prime. Think about how to prove this. We'll go over at least some of this next time. Any questions? All right, well, we'll see you folks on